Hello friends, welcome back. This video is a continuation of the series of videos on VXLAN, BGP, EVPN. And in this video we will discuss a very important topic in BGP, EVPN multi-homing, and that's related to designated forwarder election. And to explain this election process, I'll be referring to the RFC, which is RFC 7432 on BGP MPLS-based Ethernet VPN. And if you haven't read the RFC yet, I would strongly suggest you to do so. And also, before you watch this video, I will advise you to watch the video related to route types 1 and 4, as the concept of designated forwarder is related to multi-homing and precisely EVPN route types 1 and 4. The topology that we will be working on in this video is the one that you see on the screen. So we have two spine routers, spine 1 and spine 2, and they are connected to three leaf switches, leaf 1, leaf 2, leaf 3 from both spines 1 and 2. And we have server 1 in VLAN 10 multi-homed to leaf 1 and leaf 2. And from the leaf's perspective, they are attached to Ethernet 1/3 on both leaf 1 and leaf 2. So like we discussed in the video related to route types 1 and 4, Ethernet segment route, or route type 4, it serves two main purposes. Firstly, it helps in discovering other ESI members that are connected to the same Ethernet segment. So in this case, once server 1 boots up, so from the server's point of view, its uplinks, i.e. Ethernet 1/1 and Ethernet 1/2, will be configured as a link aggregation or port channel, and the downstream device, in this case server 1, will be unaware of the fact that it is connected to two different devices. On the other hand, on the upstream devices, i.e. leaf 1 and leaf 2, we will configure a shared Ethernet segment identifier, or ESI, on both leaf 1 and leaf 2. And for individuals who haven't seen my previous video related to route types 1 and 4, we define an Ethernet segment as the set of links connected from a CE to a set of multi-homed PE devices or PE nodes. And from the CE's perspective, the Ethernet segment appears as a bundle or as a link aggregation / port channel. And to visualize the concept of Ethernet segment, so if we go back to our topology, the links downstream, which is ETH 1/3 on both leaf 1 and leaf 2, connected towards server 1 VLAN 10, that will form an Ethernet segment, and we will configure or assign a shared Ethernet segment identifier on both of these links. So these links will be part of a port channel, and in that port channel we will assign an Ethernet segment identifier, and within the Ethernet segment identifier sub-configuration mode, we will assign the Ethernet segment a unique value. It's a 6-byte value that we configure, but the system software generates a 10-byte value from the 6-byte value that we configure, and it will be advertised towards the spines, so spine 1 and spine 2, which in turn will be advertised to the other leaf switches for the purpose of discovery in the Ethernet segment route, or route type 4. So that is the first function of Ethernet segment route, to discover other peers which have the same Ethernet segment configured. So the way it works is, as soon as we configure the ESI value on the leaves, leaf 1 and leaf 2, it will generate an import route target based on that Ethernet segment identifier. And when the updates are sent to the spines, and spines, as they are the route reflectors, will reflect those routes to the remaining leaf switches. So that prefix will be sent to leaf 2 and leaf 3. So the leaves or the provider edge devices where that Ethernet segment is configured, so in this case leaf 2, has the same Ethernet segment identifier configured, and it would have generated the same import route target. It will accept that update from the spines and install that update in the BGP routing table. Similarly, leaf 3 will also get the same update from the spines, but as it does not have the Ethernet segment identifier configured, and as a result it won't have the import route target generated, it will discard those updates from the spines. The second function of Ethernet segment route is to perform a function called designated forwarder election, and this process is explained in section 8.5 of RFC 7432. So the first question that one might ask is, why do we need a designated forwarder in the first place? Or what's the problem that we are trying to resolve? So let's assume that behind leaf 3 we have another host in VLAN 10 that wants to send some traffic towards server 1 VLAN 10, and as it's the first time it's trying to send some traffic towards the server 1, it won't have the IP to MAC mapping for that server. It will send an ARP request towards leaf 3, and as we have seen in the previous videos, that we send broadcast traffic as multicast towards the rendezvous point, which in our case is manually configured as spine 2, 2.2.2.2, and as leaf 1 and leaf 2 have the same VLAN to VNI mapping, i.e. VLAN 10 to VNI 10,010, spine 2 or the rendezvous point will send that multicast frame towards leaf 1 and leaf 2, and as Ethernet 1/3 on leaf 1 and leaf 2 are part of the port channel connected towards server 1, they will forward the bump traffic towards server 1. So server 1 will receive duplicate copies of the same ARP request. So this is a suboptimal behavior, and to overcome this situation, leaf 1 and leaf 2 will run a mechanism or an election process between them, which is called the designated forwarder election process. And RFC 7432 explains this mechanism of electing the designated forwarder per VLAN as V mod N, where V is the VLAN ID and N is the number of leaf switches in that Ethernet segment. So when we say the number of leaf switches with the same Ethernet segment configured, so in our example, leaf 1 and leaf 2, they have the same Ethernet segment identifier on port channel 12 that is connected towards server 1 VLAN 10. So they will form a redundancy group, and the number of leaf switches in this redundancy group is the value of N in this calculation. So N in this formula represents the number of leaf switches in this redundancy group, and the formula says V mod N generates a value which is I, and that's exactly what we will be discussing next. So if we go back to the CLI and run the command show NVE Ethernet segment, it shows us the ESI value that we configured along with the system generated 10-byte version of that value. So we configured the value 0000000012, and then the system auto assigned the remaining 4 bytes. So this is the value that we assigned, and then the system assigned 03 and then the last 3 bytes in the end to make it a 10-byte value. And this is part of the port channel 12. The Ethernet segment state is up. So the value that we are interested in is this value here, which says my ordinal value is 0. And the DF list has 2 IP addresses, which are the IP addresses of leaf 1 and leaf 2. So the way it works is, once the leaf switches receives root types 4 from these spines, it will generate a list of all the leaf switches which has the same Ethernet segment configured, and it will assign it a value based on the originating IP address. So starting from 0, so leaf 1, which has an identifier of 3.3.3.3, will be assigned an ordinal value of 0, and leaf 1, which has the IP of 4.4.4.4, will generate an ordinal value of 1 for the purpose of designated forwarder election. Now going back to the designated forwarder election mechanism, this process is run per VLAN or per EVI. So for a VLAN identifier of 10, the value of I will be V mod N. So V here is VLAN ID, which is 10 mod N, and N is the number of leaf switches in this redundancy group, and we have 2 leaf switches here, leaf 1 and leaf 2, so it will be 10 mod 2, and mod, as we know, gives us the remainder of 2 values as the output. So 10 mod 2 will give us a remainder of 0, and as we have seen from the CLI, leaf 1 with an IP of 3.3.3.3 has the ordinal value of 0. So for VLAN 10, the designated forwarder will be leaf 1. So just to reiterate with another example, so if we have to calculate the designated forwarder for VLAN 11, let's say, so if we run the same formula, which is V mod N, which gives us 11 mod 2, gives us an output or a remainder of 1, and as we can see, leaf 2 with an IP of 4.4.4.4 has the ordinal value of 1. So if we have VLAN 11 in our topology, the designated forwarder for that will be leaf 2. So let's verify this in the CLI. So we can see that we have VLANs 1, 10, 20, 500, 999 and 1234 active on this leaf switch and is forwarding on port channel 12. And this leaf, i.e. leaf 1, is the designated forwarder for VLANs 10, 20, 500 and 1234, which are even VLANs. So any even number divided by 2 will give us a remainder of 0, which is the ordinal value of leaf 1. And likewise, if we do the same verification on leaf 2, so we have the same VLANs in forwarding state on port channel 12, the Ethernet segment state is up, port channel state is up, and this leaf is designated forwarder for VLANs 1 and 999, as they are odd VLANs and they will give us an output or a remainder of 1, and this leaf, i.e. leaf 2, has an ordinal value of 1. So The leaves first assign themselves an ordinal value and then run this formula, i.e. v mod n, and based on the remainder they calculate or derive a designated forwarder per EVI or per VLAN. And just to validate data plane forwarding in our topology, we will ping from server 1 VLAN 10 across to server 2 VLAN 10. Again, they're in the same VLANs. And also from server 1 VLAN 10 over to server 3 VLAN 20. Server 1 VLAN 10 and server 3 VLAN 20 are in different VLANs, as you might have observed. This is where the concept of symmetric and asymmetric routing and bridging comes into picture. So if you haven't seen the video related to symmetric versus asymmetric IRB in my channel, I would suggest you to do so, as the difference between symmetric and asymmetric IRB has been explained along with a lab scenario. So now going back to the CLI, VLAN 10 client 1 has an IP of 192.168.10.10 and VLAN 10 client 2 has an IP of 192.168.10.20. So let's do a ping from VLAN 10 client 1 to VLAN 10 client 2. So we will be pinging 192.168.10.20. Yeah, we can ping all day long. And if we go back to leaf 1 and do a show BGP L2 VPN EVPN root type 4, it will show the root type 4 configured locally and also root type 4 that it has learned from other Ethernet segment peers which have the same Ethernet segment identifiers. So in our topology, leaf 1 has learned Ethernet segment routes from 4.4.4.4. It has done it twice because there are two route reflectors, so 1.1.1.1 and 2.2.2.2 are the two spines in our topology. And like we discussed earlier, when we generate or when we assign the port channel with an Ethernet segment identifier, it generates an import route target, which is the value here. So this import route target that you see here, RT 000000000012, is the system MAC or the Ethernet segment identifier that we assigned under the port channel connected towards the server 1 VLAN 10. And likewise, the same on the locally learned route type 4. So this is how the Ethernet segment peers connected to the same Ethernet segment discover each other. So as we can see, this import route target plays a vital role in discovering other leaf switches or other provider edge switches that are connected towards the same Ethernet segment. Now let's also verify reachability between server 3 VLAN 20 and server 1 VLAN 10. So the IP address that we have assigned on server 3 VLAN 20 is 192.168.20.10 like we see on the screen. So let's ping between VLAN 10 client 1 to server 3 VLAN 20, yeah, and like we see there is IP reachability between the two servers in different VLANs. And if you look at the update that gets sent from the leaf to the spines, we see that the update gets sent as a BGP NLRI, it says here. So it gets sent as an EVPN NLRI with the NLRI type as Ethernet segment route, and it has all the BGP attributes like the AS path, local preference, origin code, and it also sends the extended community, which is the route target value here, and this is what we verified in the CLI as well. And leaf 1, which has an IP address of 3.3.3.3 as the source for the BGP update, sends the next hop as the value 3.3.3.3 which gets added to the DF list which we used in calculating or deriving the designated forwarder like we saw a few minutes ago. And in the Wireshark capture we also see the Ethernet segment import route target that we discussed and saw in the CLI. So this is the Ethernet segment route target that gets sent from the leaf towards the spine, and this value is derived from the system MAC or the Ethernet segment identifier that we configured under interface port channel 12, Ethernet segment ID of 12, and then we assign the system MAC of this value, and based on this system MAC value we got this import route target which was then sent towards the spines as a BGP update. So friends, this was an in-depth explanation along with lab verification of Ethernet segment route or route type 4 in VXLAN BGP EVPN multi-homing, and I hope this has helped in clarifying your concept of Ethernet segment route. So friends, if you like this video, give it a thumbs up. If you haven't subscribed to my channel yet, please hit the subscribe button. Please share this video with your friends and colleagues. And if you have any feedbacks, comments, suggestions regarding this video, please leave it in the comment section. And if you found this video helpful, please support this channel via Buy Me a Coffee. The link is in the description. So friends, thank you very much for taking the time to stop by my channel today. So until next time, take care.